Hi and hello everyone. Having seen the distributions which are more general than exponential, that is the Erlang hyper-exponential or in general a general phase type distribution. Now we will look at a couple of models utilizing the this kind of distribution. So, mainly we will be looking at only the Erlangian model. So, basically we will look at the Erlang based queuing models and how one can analyze that queuing model is what then we will see in this lecture. Now, the ideas that we gain from here is in general applicable to a general phase type distribution. And you can see how we are getting back the Markovian nature in some form. Everything it will be explicit in this discussion. But since we are not going to see a model which is based upon a general phase type distribution, the same idea is what will can be extended to a general phase type distribution. And hence you pay attention to how we are dealing with this, right. So, how we are constructing the Markov chain in this particular case, right. Now, you see what we start with is a model which we call it as Erlang service model, right, meaning that we have an MEK1 queue, right. So, what do we have? All the assumptions of MM1 model in equilibrium are in place, except that the service time distribution now is replaced with an Erlang type K or EK distribution with mean 1 by mu. Okay. So, we are retaining this mean 1 by mu for ease, right. So, that is how then we have defined this Erlang type K distribution as well, and this is what is the use or the utility that comes handy here. Okay. So, this is the difference. All assumptions of MM1 are in place except that the service time distribution now it is replaced by an Erlang distribution rather than an exponential distribution, right. But since Erlang you can view it as if sum of IID exponential. So, the service time duration which is basically the EK distribution or Erlang type K distribution may be thought of as if it is consisting of K independent and identical exponential phases or steps or stages. Generally the phases is what is the word used. Now, each of these phase following an exponential distribution with mean 1 by K mu. Okay. As we already pointed out, even if there is no such phases, it is always convenient to think this way, right. Now, since the overall service rate is assumed to be mu, the rate of each service phase is K mu, that is what we have here. Now, this particular system can be described by a two-dimensional continuous time Markov chain or two-dimensional Markov chain whose state space is given by this pair n comma I, where n is taking greater than or equal to 0 and I is from 1 to k. And what does this n denotes? This n denotes the number of customers in the system at any given point of time. We are looking at in equilibrium. So, this is what is the, and I is the current phase of the service for the customer currently in service. So, what is the current phase? Because you know that this is K phase services are there for this Erlang service time distribution. Now, for convenience the phases are numbered backwards, meaning K we denote it as if it is the first phase of the service and 1 is the last phase of service, right. So, essentially when you are looking at here, right, you see that this total is Erlang, but we call this as the kth phase and so on, and this as the 1th phase and the service time. So, this total duration is what is my EK, right, that is what you have here, and each of these has a rate K. So, this is what we are looking at it. So, the first phase is K is what we are saying and 1. Now, suppose if it is in say some ith phase, meaning that I more phases to go in this service, that is what it would mean, right. So, when it is in 1, at the end of this phase his service is getting completed, that is how we have to view it. So, this is important to understand that in order to describe this Markov chain and how it behaves and so on, right. So, that is the part. For that convenience, just any time if it is in phase I, mean I more phases are remaining. It is no different that if you order it in the usual way, then it will be k minus I is what I plus 1 you have to write. So, it is easier to write it I. So, that is what is given. So, suppose for example, if this is n equal to I, so if you want to count the total number of phases that is remaining for all the customers who are currently in the system, then it will be something like this, n minus 1 times k plus I. So, if this is phases are ordered numbered differently, then this will be changing, that is the difference, right, fine. So, that is what we have here. So, this is the Markov chain, 2-dimensional Markov chain. We can call it one as the number and the other dimension as phase of the current service which is undergoing, right. So, that is what is this Ni. Remember this N and I. Now, let us look at how this system would behave and let us try to draw the state transition diagram of how the system will behave in this case. So, look at this diagram. Okay. What happens, for example, when the system say at 0, since there is no customer, so you do not need to depict this phase. Okay. As such here, though we have written it in this phase, so 0 all the phases are, you can group it as a single, probably I could have written in that way, that 0 union of this is what is going to be, where for n greater than or equal to 1 is what is going to be this S. Okay. What I mean to say is that I can make this as 1 and this union 0 is the state space. Okay. That is the probably the appropriate way, does not matter, fine. That is what we have it here actually in this diagram. Okay. So, what we have here is 0 when it is in state 0, which means there is no customer, it is the system being empty. An arrival with rate lambda will bring this to this particular state, right. We said that there is one customer in the system and the current the phase of the service for the current customer. Since there is only one customer, he will be in this particular state, he will be directly into the service and his service will start. So, the current service being in phase k, because we said we are numbering the phases backwards, right. Now, let us see from here onwards, like from in 1k, right, if there is a one phase is completed, one phase of his service is completed, then it will move to 1 k minus 1, then one more with which is with the rate k mu. Now, from 1 k minus 1, it will move to 1 k minus 2 at the same rate k mu when that phase is completed, provided no arrival happens during that period, and so on. With from 1 3 it will go to 1 2, and from 1 2 it will move to 1 1, and at the end of service completion of this phase, assuming that there is only one customer and no arrival happens, if the service completion happens, then it will come back to 0, right. So, this is what one customer he comes in and then nothing happens while his it means no arrival happens during his service time, then the system will move from here all up to this and then it will come back here, right. Now, on the other hand, suppose if there is when it is in 1 k, if there is a customer arrival, then the system will move to 2 k, right. The number of customers will become 2, the phase of the service of the customer who is currently in service will remain as k, right. Now, once in 2k, then like what had happened in this column, like it can also happen in this column, right. It will go along this line. Now, at this point of time 2 1, if the service is completed, so there are two customers, the current customer is getting service in he is in phase 1. Now, at the end of his service with rate k mu, this blue line here, right, this system will reach to 1 k, right, because there will be one customer and for that customer the service phase will be in k, right. So, this blue line. Now, just like here the horizontal movement happened from 1k to 2k, a horizontal movement can happen from 1k minus 1 to 2k minus 1 if there is an arrival at this phase or an arrival in between or an arrival 1 3 or an arrival 1 2 or an arrival at 1 1. Even when it is in 1 1, if the arrival happens, it will take you to 2 1, and at the end of that, if the service completion, it will come back to 1k and go on, right. So, once you understand this, how the system is going to behave, at what is the rate. Now, you see what is the advantage that we have done, because we are expressing the Erlang distribution as consisting of k phases of exponential. We have this depiction here, this whole column being expanded for the number of phases. Otherwise, you have seen in a birth death cases, simply you would have as one single line horizontal to depict the states where, so this is 0, this is 1, basically this whole thing will be shrunk to a single state with 2 is the number of customers, 1 as a number of customers, 2 as number of customers, 3 as number of customers, and that is what we have seen. So, basically what we have done, if it is Erlang, then this state, this, suppose if I call this column as as if the number of customers, suppose if I write here, so this is 1, this is 2, so this is 0, there is no problem, this is 3 and so on. This is what is the number of customers. So, this is the number of customers is what then we have here, like this 0, 1, 2 and so on is what is the number of customers, right. So, this one only is being expanded into k phases, expanded into k phases, expanded into k phases, and from how the transitions will happen is what then is depicted here, right. So, this is what is important. So, this is what is a state transition diagram, a rate diagram for this MEK1 model, as you can see here, right. And you know the complexity now, how when such the number of phases increases, what would be the complexity of this, okay. So, that is what it will increase, right. This is k, depending upon what is the value of this k, right. That is what we said, that as long as it is reasonable, like one can handle it, but if it becomes too large, this k is even in this particular case, so this becomes very complex system. Anyway, so we have a way to handle, we will come back to that, fine, right. So, this is the depiction of this. So, now here we have one type of behavior for this state 0, one type of behavior for this state, and one type of behavior for the remaining state in this column, and one type of behavior for this group of states, and all other states will behave in a similar way, right. So, accordingly, if you write down the rate balance equation, you will have for one each group. Say for example, this one, if I look at it, it is for the state 0, right. You can see lambda p naught equal to k mu p 1 1, right. Lambda p naught equals k mu times p 1 1 is what you are writing it here, that is the first equation. Now, you look at state 1k, which is this. So, what is happening? There is a lambda going outside, there is a k mu going outside. So, it is the flow out of the state is lambda plus k mu times p 1 k, right. Lambda plus k mu times p 1 k is the flow out of the state, and to flow in is lambda times p 0 plus k mu times p 2 1, right, this blue line here. Right, all these blue lines depict in this diagram the service completion phases, and all these magenta ones are internal phase completions for this Erlang, and this oranges depicts the arrivals, right. Now, for this 1k, these are the other two terms, k mu from p 2 1 and lambda from p naught, right. Now, this is for states 1 for I between 1 to k minus 1, which means this particular states. For this group of states, you can see all the states will behave, there is a outward lambda plus k mu, which is coming here in the left side, or p 1 y, and the right side you will have only k mu times p 1 I plus 1, right. So, from k1 I plus 1 there is only 1 which is coming inside each of these states, that is what you are looking at it here, right. So, that is what this k, and this nk for the kth one, right, this state for n greater than or equal to 2, that means for this last row from 2k or 3k for this particular state, you will have this as the equation in a similar fashion, and for all other states in general for n greater than or equal to t and y I from 1 to k minus 1, right, which means from all this, for all these states you would have this general equation which is the first equation that you will have here, right. So, that is the flow balance equations. Okay. Now, you know, like though you have written down the flow balance equations, now if this is reasonable system, obviously then you will be able to handle it and you can get the solution, right. But at least you have written down, now you can adapt appropriate method to do this. But remember, these equations are not that easy to handle due to their bivariate nature, obviously. But what comes handy to us in this queuing system is that we can relate this Erlangian service queue to the bulk arrival model that we have considered earlier, right, with a constant bulk input, okay, which is mk m1, where each unit brings in k phases, capital K equal to small k here, and the phase service rate is mu, in that case is replaced by k mu. So, you can make an equivalence, right, as if right, it brings in each arrival, because if you look at the number of phases, right. So, we said that, you go back, we said that number of phases here, right. So, now if this is the state, now each arrival will bring in k, and if I look at this number of phases, that is where this transformation, if I make the transformation, it might be useful, for which only this relationship is, or this equivalence between these two systems are important, is that each arrival you can think as if you know, it brings in k phases, okay, which you in the bulk you can think of as if it is basically it brings in k arrivals, right. Each of them, now the rate is k mu, not mu, that is you have to remember that, okay. So, that rate is k mu, not mu, because each of these phase requires k mu as the rate. So, we can utilize this equivalence of MEK1 to MKM1 with a constant phase, right, to get the performance measures easily, right. So, to determine the average weight in the performance, average weight in the queue, which is WQ for MEK1, observe that the number of phases is equal in MEK1 is the same as the average number of customers in the analogous XM1 queue, which is equal to this, right. But in this Erlangian model, the mu in the original the bulk arrival model needs to be replaced by k mu. So, the rho now it becomes this quantity, k lambda by mu was the original rho. So, now this will be k lambda by k mu. So, this rho becomes lambda by mu here. Now, if I plug that into this expression, then this is what I would get, where my new rho is lambda by mu. For this model, rho is lambda by mu, that is the utilization, because your arrival rate is lambda and the service rate is mu, though it is distributed as Erlang. So, the rho is lambda by mu is the utilization of utilization factor traffic intensity for this particular system. So, if with that change, that is a change that you have to adapt. So, if when you adapt that, then your WQ would become this. So, basically we considered this MX-M1 model, and we also considered the special case where X is a constant batch size, and in that case we arrived at this expression, and say we said that this is the quantity corresponding to MM1 and it is multiplied by this factor, right. Now, what we have to make adjustment, because now in the row we have to make adjustment where mu is replacing by k mu, which will bring you this as your new row, and with that new row this is your wait in the queue, which is the average waiting time in the queue. Now, once we have this, then you can LQ, you can compute it as lambda times WQ, which is equal to this, L as LQ plus rho and W as L by lambda. In the usual way, you can get the other performance measures, right. So, that is the change that you have to remember. So, you see how we are making the equivalence, we are making one system which is equivalent to the equivalence to another system, and we are getting done with our work into this case, okay. Getting the performance measures. Of course, other performance measures also you can obtain if you know for that. You can always relate these two systems with this change in mind. Now, we can also obtain the steady state probabilities in this situation. It is not that difficult. So, what we do is that we make this transformation which we observed earlier, which is what we made use when we make this change here. Ni can be transformed to this in a single variable system, right. This n and I am mapping to this quantity, that is all we are doing it. You are mapping Ni to this quantity. Now, this represents the number of phase left in the service, right. But one thing you have to remember between when you are making the equivalence between this MEK1 and this bulk arrival, the service completions here in the MEK1 model does not correspond to customer departures. That's you have to remember it. Keep that in mind. Okay. Whereas in bulk queue, each customer departs, but here it is the customer is not getting departed. That you have to remember that. Okay. Once you make this transformation, then the whole set of equations that we have written down can be mapped to this set of equations with any p, we are just writing it generically. So, with any p with a negative subscript, if it comes for any of these quantities, when you substitute in this, would assume to be 0. So, you assume that is not existing, right. So, we are writing for the general one in a way, right. So, this is the set of equations. Now, again this set of equations, if you start with n is equal to 1, I is equal to 1 and then write this sequentially, write this set of equation in explicit form and sequentially, then you will end up with this set of equation, right. So, that is what you have to observe here. Once you do this, the notations may be here like this, but you start with n is equal to 1 and I is equal to 1, then I is equal to 2 and so on, then n is equal to 2, I is equal to 1 and so on. When you write sequentially in a simple, you will end up with this set of equations for n greater than or equal to 1. And for n equal to 0, this is what is this equation. So, this set of equation is what you would end up with ultimately. Okay. Now, what does this gives? This set of equations is the set of equations for the bulk arrival queue with a constant batch size k and service rate k mu. This is what is basically is the equation for that. So, we already said that how one can solve for such a system in the case of bulk arrival queue. From this set of equations, then you can obtain this expression which is same as the one that we have obtained earlier, and using the condition p of 1 equal to 1, now you can compute p naught which is to be 1 minus rho for rho lambda by mu, and p of z would then be equal to this. Now, from which, right, if you can, this is basically a polynomial in k plus 1 right. So, if you can expand this expression as a power series after writing down this through a partial fraction expansion, that can be done if you know the roots of this equation. You can in theory obtain this Pn. Okay. Once you obtain this Pn, we already said that when we discussed about this bulk arrival queue, for reasonable values of k, this is possible to obtain this series, right, and we have also exhibited one example. So, that's the idea, right. One can in theory obtain this Pn. Now, once these Pn's are obtained, now remember this Pn's that we obtained here, it gives the probability of the number of phases in the system. It does not really give this Pn is number of customer in the system, right. Now, if Pnc for the customer, if we denote Pnc as the probability that the number of customers in the system is n, then we know Pnc can be written in terms of this Pn using this expression, right, any of these phases, right, any number of phases from n minus 1 times k plus 1 to up to this nk, all these probabilities if you sum up, you will get, all of this would correspond to the number in the system, right. So, as you go back, so all of these probabilities would correspond to the number in the system being 2. So, if you sum all these probabilities is what then you are going to get, and these are the one which we are summing as such in this expression here, right, in this expression here to get the number in the system, right. Which is what you can obtain. Once you obtain this PNs, then you can obtain this PNC. Now, as a special case, if I assume k is equal to 1, then what I should get? I should get an MM1Q, right. So, in this particular case, my P of Z will become this, where in observing that 1 is always a root here. So, I will arrive at this expression, which is what we have obtained as an expression of the PGF of in MM1Q, which gives me this PN, but here Pn and Pn, the number in the customer, this is number in the phase is 1 because the number of phases is 1. So, this is exactly equal to PNC as well. So, this is true for this case. Now, let us look at couple of examples. Typical, suppose there is a service system to which customers arrive according to a Poisson process with mean rate of say 16 per hour. The mean service time is 2.5 minutes with a standard deviation of 5/4 minutes, right. So, that tells me that this is not an exponential. So, it is thought that Erlang distribution would be a reasonable assumption for the service time distribution. So, once you know mean and variance and you think that Erlang you want to fit in, okay. Now, the question was, for example, typical, how long a customer on average must wait until getting into the service, wait in the queue, and how many customers are waiting for service, which is again number in the queue, average number in the queue. So, the appropriate model, since you want to fit Erlang distribution, it is some MEK1 model for some EK. There is a service system which has single servers, which we have not mentioned, but of course, that you can assume that this is a single server model, okay, single server model is what then you are assuming, okay. So, the appropriate model is MEK1 model. So, we are given what is lambda, we are writing 16 per hour. So, 16/60 per minute, and this is 1 by mu is 2.5 minutes, okay. Now, sigma squared is basically for this EK distribution is k 1 by k mu square, mu is given, substitute it, right. So, this sigma square is given to be 25/6, right, because standard deviation is 5/4. So, mu is I already know it is 5/2. So, this I substitute and I will get k is equal to 4. So, given mean and variance, I can always compute what is the number of phases that needs to be there to fit this model. Suppose if it comes approximately, then you take the nearest integer to be the appropriate value of k. Suppose if it comes to 3.7 for example, then you make it as 4. If it comes to 4.2, then you take it as 4, right. So, that is what you would take generally, if that is an approximate fit that you are making it. Now, once we identified that, then we can obtain what is rho, which is lambda by mu, right, which will give me 2/3. Now, with that, now I already have the expressions for the performance measures, right, WQ, LQ, L, and we wanted WQ and LQ in this particular question, but you can ask the other question as well, right. So, this is basically LQ and this is WQ, simple, right. So, you can obtain in such scenarios. Now, let us look at another example. Suppose there is a production or manufacturing process in which the components are going in sequence, and after the one stage, of course, there is a quality control is being employed, and in the quality control test, repairs are detected, and the repairs occur at the rate of detected at the rate according to a Poisson process with 18 per hour. Okay. And the repair facility has 2 specialists or 2 repairmen, and each can repair the component to make it correct and so that it can be pushed into the next stage, and they will take on an average of 5 minutes with the repair time being exponentially distributed. Now, the company also has an offer from a manufacturer of a machine which gives the following. So, that alternative option is they can lease that one machine of that, and that can repair the components in exactly this much time, right. So, it is that is what 2 and 2/3 of the minute, right, it can repair that, and there without in exactly this much time, and no variation in repair time is what being promised. Now, assume that there is no labor issue even if you remove this specialist, because they can be employed elsewhere in the company, and the cost of employing these two specialists to repair this, and their meaning in their salary and other benefits that you accrue to that two specialists would be roughly equal to the cost of leasing that machine, assume. So, there is no cost factor that we want to bring in. So, we are assuming that these two costs are the same. Then the question is, should the company lease the machine? Should you go for leasing the machine, or you retain with this? So, you want to make an analysis. So, how do you do? So, you need to compare W and L under the two alternatives. What is the alternatives? The first one is an MM2 model, right. Arrivals happen according to a Poisson process, service is exponential, and there are two servers, versus an MD1 model where arrivals again same Poisson. Only thing is the service is what you want to replace with a deterministic one D and with a single server, right. This is what is the question. So, MM2 versus MD1 with the given parameter you have to analyze. So, for the MM2 you can compute lambda to be 18 per hour and mu is 2.5 minutes. So, it is 12 per hour is what is MM2, and this would mean my WQ is basically 6.4 minutes and W is 11.4 minutes and L is 3.42. You can obtain this using the usual formula of MMC. Now, for MD1 we did not deal explicitly with the MD1, but we know that in the Erlang distribution, if I take and if I let the number of phases tends to infinity, then I am going to get a deterministic situation, right. So, we use that idea that limit of MEK1 would be MD1 model. So, compute lambda, compute mu, which is 22.5 because that is what is here 3/8 per minute. So, this is what is per hour. Therefore, WQ which will be equal to this in this particular case. Now, if I let k tends to infinity, so this quantity tends to 1, the remaining will give me this. Now, I already computed lambda and mu I have. So, I just substitute it here to get to 16/3 minutes, and W is 8 minutes and L will give me 2.4 minutes. So, if you see my W in this particular case would be 11.4 minutes here, whether here it is in the, if I use the machine it is 8 minutes. The number in the system, which is number of machines down or number of components that are waiting at the in front of these two specialists for it to put it back is 3.42, and whereas it is 1.4. Of course, if this is more, obviously this is going to be more, that is obvious, but you can see that what is the quantity, what is the magnitude to make a call. Whether this difference is sufficient enough to warrant if you want to lease the machine. Now, remember here we did not bring in the cost factor, but if I bring in the cost factor, now the decision is the leasing the machine is preferable, because it gives me lower waiting time in the system and lower number of components being repaired, right. But if the cost factor, if it is different, then accordingly then you have to weigh between these two options to take a call and so on, right. So, this is a simple and typical example that one can use to get to this one. So, this is about MEK1 model. The next model that we will consider is basically Erlang arrival model or EKM1 model, right, EKM1 model. So, what is that? It is except similar to the previous model, but now the arrival is considered to be an arrival is happening according to a process where the inter-arrival times are Erlang distributed with phase k and with mean 1 by lambda, the rest being as usual service is exponential with. Like the previous model where we made equivalence between MEK1 model and the bulk arrival, here EKM1 model and the bulk service model with a constant or fixed batch size model, one can make an equivalence, and that is the in a similar way one can view it, right. So, EKM1 model and MK1 model can be made equivalent. We can think an arrival as if it is bringing in k phases, each with mean k lambda before actually entering into the system. And even if it is not the case, you can think Ek as if it is in this manner, so that it is convenient, like in the case of MEK1 model, it is convenient device for analysis. Here the phases are numbered now frontward from 0 to k minus 1, this is for convenience. Okay. Now, if I denote P and P denote just like the Pn in the previous model, here P and P denote the number of arrival phases in the system in steady state, right. So, the number of arrival phase system includes k phases for each customer who has already arrived but not yet departed, as well as the completed phases corresponding to the next arrival. Means arrival before entering into the system, right, before actual entry it is marked into the system, it has come to some outside which is again part of the system, you can think, and then it is going through that number of phases. We say that this is officially arrived, even though the customer has not officially arrived into the system, but he has arrived to the system and he is going through that arrival phases. That is how we are viewing it actually. Okay. Then once we have this P and P, much like the earlier case, this Pn now with the number of customers being n in the steady state, which we said P and C there. You can also, if you want that, you can attach a C here, no problem, for that number of customers in the system can now be given in terms of this phases, right, much like the same way. Okay. So, this system then is identical in structure to the full batch bulk service model. So, the rate balance for P and P are identical to the rate balance for Pn in the bulk service model, not elsewhere, except now again lambda is now replaced by k lambda and of course capital K by small k, which we already did. Therefore, we will get to this expression in that particular case, where R naught is a single root for this characteristic equation, like in the earlier case, this C I need not, because we can always assume 0 to be nothing, okay, right. So, this characteristic equation, now since we already once we obtained this, then we know already this number in the system. So, the number in the system, which we can call it as P and C, would be given by this, which is equal to this, which is equal to this expression, and P naught equal to obviously 1 minus rho is what then you would see, right. So, one can obtain. So, by making equivalence between the EKM1 model and the full batch bulk service model with lambda replaced by k lambda, then you will get this as the equation, and the single root is what is R naught, and in terms of R naught you can get the number of phases probabilities, and from the number of phases probability, number of customers probabilities, you can obtain it, which will be sum of this, which will end up this here. So, here if you see, if I just forget about for the moment rho, this is again is in a geometric, which is the form with R naught to the power k as the quantity. In that form it is geometric, and with rho, and this is 1 minus rho, that is what you know. This is common in general in GM1 model, as you would see later when we handle that. Okay. Now, once we have this one P and C here again has a geometric form, but this as with R naught k, right. So, this is with R naught k is what as the geometric parameter instead of rho. If you compare with MM1, then you can obtain the performance measures in the usual way, right. You can obtain L to be rho by 1 minus R naught to the power k, and LQ as L minus rho, W as L by lambda, WQ as W minus 1 by mu, and so on, right. So, this is the usual way performance measures you can obtain. You can even obtain waiting time distribution, which will be much similar to the MM1 case and so on. But we will not go into that, but rather we will see an example. So, system is arrivals occur into a single server queuing system with E2 distributed inter-arrival times with a mean interval time of 30 minutes. Mean is given, E2 number of phases is also given. So, the service times are exponentially distributed with mean of 25 minutes, right. Now, you can determine the steady state probabilities, you can determine the expected value measures which will give you the effectiveness of this particular system, right. So, what is given? Given is lambda is 2 per hour, mu is 25 minutes. So, 12 by 5 per hour, right, and k is equal to 2. So, with that I can write down the characteristic equation which will be equal to this, and knowing that one root of this equation is going to be 1. So, I can extract that to arrive at this. Now, this is the quadratic in R which we can find 2 roots, which is minus 3 plus or minus under root 69 by 6. Now, out of which only this root with the plus here is going to be in this region 0 1. So, that is the R naught. Now, once we have this R naught, we want number in the system, number of customers in the system, which is given by this expression. Now, R naught to the power k, k is 2. So, this is my R naught. So, the R naught 1 minus half that is this, and R naught is this to the power n minus 1. Now, these and this minus 1 or the one term of here would give me this with it. So, this is the form of PNC with P naught is equal to 1 by 5. Now, you can check that if you sum all these things for n greater than or equal to 1, you will end up with 5 by 6. So, total probability is 1 that you have. So, the mean system size L is given by this as we obtained here, which we can obtain in all these expressions as per your requirement. So, this is about the E2M1 model, which again what we are seeing is these models can be analyzed using Markovian theory, meaning that you can write down the red balance equations and you can solve it. But while doing that, you observe this MEK1, you do not need to solve it separately. You can make an equivalence between the corresponding bulk service, bulk arrivals models whenever EJ or EJM1 or MEK1 models are considered, and you use that equivalence to directly get the final solution here, right. But that is what we have done in this particular case. Even if you have EJEK1 model, suppose both of them are Erlangian. Now, 2 dimension is not sufficient. Now, you need to go to beyond 3 dimension you have to keep, and then you have to work. So, thing is that model gets complex, but one can do analysis Markov. In general, right, for a phase type distribution, like this idea can be utilized, right. Once you have this, then you can write down the Markov chain, and then you can write down the red balance, and you can then onwards see how you can solve this. Okay. So, a sophisticated method handling the matrix form of this is what would be required. So, that is what is done when you are handling with phase type distribution. So, all these things you can represent in terms of phase type distributions, as you know, right. So, you take a generic representation of phase type in terms of alpha and q tilde, as we have described in the earlier, right. So, in that particular case, using the matrix theory, like you can represent things in the matrix form, and you can deal with in matrix form in a much compact way. It is only compact way. Again, if you expand it, it will be messy, but in a compact way you can handle it, and that whole lot of idea is what is called matrix geometric analysis or matrix analytic methods and so on. That anyway, which the starting point will be the taking that distributions of inter-arrival time or service times as phase type distribution, then you directly employ those kind of methods. That is what is probably the current standard in literature that you would find when you are dealing with more complex models, but they are still within the Markovian framework. That is what is you need to remember this. So, this is just an exhibition of how one can utilize basically non-Markovian distribution. You represent it through in terms of exponential, so that you can still utilize and within the framework of Markovian models, and analyze you can analyze the models in usual way as you do for a Markovian model. Okay. That is what we illustrated with these 2 Erlangian models. We may not consider any more of this kind of models, but we may generally later on will deal with the general distribution itself, how one can do, we can do that. Okay. So, with this we end this discussion of this Erlangian queues at this level. Thank you. Bye.